Hi everyone, today a video on mechanisms for A-level chemistry. So the first thing really to say before we go into what a mechanism is to talk about what a chemical reaction is. A chemical reaction is a process in which chemical elements or compounds, i.e. what we call the reactants, form new compounds, what we call the products. And these reactions involve the transfer of atoms and or electrons. Now these reactions can be between different molecules, probably what you're most used to seeing, what we call an intermolecular, between different molecules. That's that example of this nucleophilic substitution between the potassium hydroxide and this very long chain bromoalkane. Or they can be within the same molecule, something we call intramolecular, within the molecule. And so this same nucleophilic substitution can happen if we have the OH group and the bromine group attached to the same molecule, as we show at the bottom there, to form this 5-membered cyclic ring with an oxygen in. Now a simple change of state, for example, if we have something that melts or something that condenses, is not a chemical reaction, it's a physical change. A chemical reaction must involve the formation of new chemical species. So if we think about, for example, ice melting to water or water vapour condensing to liquid water, these don't produce technically new chemical species, it's still H2O, it's still water, just in different physical states. A chemical reaction has to actually involve the formation of a new chemical species. There has to be rearrangement of atoms going on. Now in general, molecules repel each other, right? We have these molecules that are largely full of electrons, and so lots of negative charge, all kind of repelling each other, and they need to overcome a barrier with a minimum amount of activation energy to react. So remember that our activation energy is this minimum energy that we need to start breaking bonds for a successful collision to occur. And you've probably seen some of these enthalpy diagrams or energy progress of reaction diagrams. We have energy up the y-axis, sometimes enthalpy. Along the x-axis we have the progress of the reaction, sometimes called the reaction coordinate. And we can label our reactants, we can label our products. We generally show a curve moving from the reactants to the products. We have our enthalpy change, or sometimes our Gibbs free energy change between the reactants and the products. We draw that from our reactants going down to the products. That's our enthalpy change. In this case, this would be an exothermic reaction because energy has been given out. The products have less energy than the reactants. And then we can draw our activation energy. Remember that our activation energy is always positive. You can think of it as the hill that we have to get over to initiate our reaction. And so we draw this from the reactants to the top of the curve. And of course, the top of the curve is called the transition state. This is the kind of in between reactants and products. It's the bit where we have some bonds being formed, some bonds being broken. We're exactly kind of in the middle between reactants and products. Typically, it's not a species that actually exists. The actual chemical species that exists is called the activated complex. The transition state is our energy maximum point. And so molecules can be brought together either by charge attraction. That seems very simple. If we have a positively charged electrophile, a negatively charged nucleophile, they're going to be brought together by simple electrostatic charge attraction. Or they can be brought together because of favourable orbital overlap. And this is because bonds form from the overlap of orbitals. So if that orbital overlap is very, very favourable, it's likely that a reaction will occur. So then we start to look at what a mechanism is. So a reaction mechanism is a snapshot look at how the bonds are broken and formed in a chemical reaction. And what we're considering most of the time is how the electrons move. Essentially, if we could take pictures of every step of a reaction, this would be the same as writing a mechanism. If we could get down to a molecular scale and have a camera that took a photo quick enough to be able to see every single little change that goes on in our reaction, this would be the same as writing our mechanism. And so it's the step-by-step sequence of what we call elementary reactions. These are kind of single change, single collisions reactions by which the overall chemical change occurs. So if I add together all of these little step-by-step elementary steps, I should end up with the overall chemical change. And mechanisms are often used in tandem with kinetic analysis and rate laws in order to deduce how a chemical reaction proceeds. So by using the rate law, we can see typically maybe what the rate determining step of our mechanism is, and we can propose a mechanism and then see if the rate law and the kinetics match what we would expect for that mechanism. Now to represent how electrons move, we're going to use arrows. A full arrow, that is an arrow which has a normal sort of head on the arrow, shows the movement of an electron pair, 2 electrons. And this is how we're going to see most of our arrows in these mechanisms. There's a very small amount of mechanisms where we have to use a half arrow, or sometimes called a fishhook arrow. This is an arrow that only has one half of the head of the arrow, and this shows the movement of a single electron. So that's very important when we look at radical reactions. And so the majority of organic reactions can be considered as bond making and breaking, and they normally involve a nucleophile and an electrophile. And this goes back to this idea of favourable orbital interaction. The other set that doesn't involve a nucleophile and electrophile are the radical reactions. But the majority of them is bond making and breaking involving a nucleophile and an electrophile. So let's start to think about what these nucleophiles and electrophiles might be. A nucleophile is an electron pair donor. It forms a bond by donating both of its electrons to an electrophile. Now, our nucleophile could be negatively charged, it could be neutral, or it could just be something that contains high electron density. But good nucleophiles have very high energy orbitals. So, our nucleophile may have a non-bonding lone pair of electrons and be neutral. These ones that you're more likely to have seen include ammonia, amines, water, alcohols. These all have lone pairs of electrons, but they're overall neutral. And some other ones that you may not have seen before, triphenylphosphine and dimethyl sulfide. While they're based off slightly different elements, you can still see that they are overall neutral, and they have lone pairs on them that can be used to be donated. Now actually the triphenylphosphine and the dimethyl sulfide are better nucleophiles than the nitrogen and oxygen based ones because they have higher energy orbitals. If you look at your periodic table, you'll see that nitrogen and oxygen are in period 2, whereas phosphorus and sulfur are in period 3. Because they're in a higher period of the periodic table, they have higher energy orbitals. A nucleophile may also be anionic. It might have a negative charge that comes from lone pairs. So we can have our hydroxide anion. And here I've shown the full kind of 3 lone pairs that would be on a hydroxide, the oxygen of a hydroxide ion. Normally though, we just simply draw that out as OH with a negative on the oxygen. We have our bromide ion, for example. That could also be a chloride ion or an iodide ion. Here we have 4 lone pairs, essentially. Remember that if we take a normal bromine atom, 7 electrons, we add an electron to this, we end up with now an octet on the bromine, and it's negatively charged, so it's the bromide ion. Again, typically we don't draw out every single one of these, we just write normally as Br-. Or we can also have the cyanide anion, which is Cn-, with the negative charge and the lone pair being on the carbon. Now in all of these cases here, the negative charge is depicting a lone pair. And while they're not drawn specifically on this slide, I normally tend to also draw a lone pair and also the negative charge. Now a nucleophile could also not have lone pairs, but it's still electron rich. So this could be, for example, the pi bond of an alkene. We don't have a lone pair in an alkene, but the CC double bond, the pi bond, is very electron rich. We have essentially more electron density than we would in just a normal CC single bond. Another example is if we have sigma bonds to electropositive elements, so single bonds to electropositive elements. And the reason why this makes it a nucleophile is it raises the orbital energy. Go back to the very start of this slide, I said that good nucleophiles have high energy orbitals. And so an example that you've probably seen is the borohydride anion. You've probably seen this from sodium borohydride, the reducing agent, being used to reduce aldehydes and ketones down to alcohols. But what you might not have realised is that it's actually acting as a nucleophile. So typically we have the borohydride anion, BH4-, but the really key distinction here is that actually the negative charge here doesn't represent a lone pair. If we think about how we've formed BH4, we've taken BH3, borons in group 3, group 3. We have our 3 electrons, they've formed 3 covalent bonds to our hydrogens. So we have 6 valence electrons on our boron, it's electron deficient. We have a hydride anion that's made a dative covalent bond, giving both of its electrons to the boron. So an H- giving both of its electrons to the boron. This creates our BH4-, our borohydride anion. But our boron, while it has a negative charge, it doesn't actually have a lone pair. We have 8 electrons, but they're all used up in bonding. We have 4 BH bonds, that's 8 valence electrons. We don't have any non-bonding lone pairs. So the key thing here is to never draw an arrow from that negative charge, because the negative charge does not represent a lone pair. The actual nucleophilic bit of that molecule is one of those BH bonds. When we think about drawing our nucleophiles, we always have to think, well, where is the electron density? For a neutral species like at the top, the ammonia, the amine, it's very clear that it's the lone pair. For our anion that has lone pairs, as I said, typically, hydroxide, bromide, we draw an arrow from the negative charge because we know that in our mind, the electronic structure of that is that it's a lone pair. We have to be really careful and always make sure we have the electronic structure in our head for something like the borohydride anion, where the negative charge doesn't represent a lone pair. So we have to draw it from one of the BH bonds. Now, examples of electrophiles. Well, an electrophile is the opposite. It's an electron pair acceptor. It forms a bond by accepting both of the electrons from a nucleophile. Now, it can be positively charged, it could be neutral, or typically it contains some region of electron deficiency, quite often a delta positive atom. And converse to the nucleophiles, which were good if they had high energy orbitals, good electrophiles have low energy orbitals. And actually what we look at for good orbital overlap is typically the highest orbital of our nucleophile interacting with the lowest energy orbital of our electrophile. And typically these are very, very well matched in terms of energy, and therefore we get good overlap of orbitals. So an electrophile may be charged or neutral, but it contains an empty atomic orbital. So the simplest example of this is a proton, H+. We start with our normal hydrogen. This has a 1s orbital with one electron in it. If we make it a positive ion, we remove the electron, we now have an empty 1s orbital. More common examples might be aluminium trichloride or boron trichloride, for example. This is where we have elements that are here in group 3, so the aluminium and the boron. As I said, likewise in the BH4 example, to make that we started off with BH3. That would also be an example of this with an empty p orbital. But in these cases here, the AlCl3, the BCl3, we have our element in group 3 that has 3 electrons, say the aluminium, 3 chlorines which each donate 1 electron in the covalent bonds, so we have 6 valence electrons around our aluminium. And then that's all of the electrons we have. We don't have the normal 8 for the octet, and so we have an empty p orbital on either the aluminium or the boron. And so these are trigonal planar molecules that have this p orbital that is at right angles orthogonal to that plane. However, there's not many actual species when we do these kind of reactions that have completely empty atomic orbitals. It's more commonly seen as having a low-lying orbital that can accept electrons. And when we talk about having a low-lying orbital, what we really mean is it being bonded to an electronegative atom. And by doing that, it lowers the orbital energy. So this could be an electrophile that has a double-bonded electronegative atom, so ones that you'll have most likely seen, an aldehyde, a ketone, an acid chloride. Here we have our delta-negative oxygen in our carbonyl group. And therefore, because we have this polar CO bond, this dipole, we end up having delta-negative on the oxygen and therefore delta-positive electron deficiency on the carbon atom. And so those examples all contain a delta positive carbon, an electron deficient carbon, and that makes them electrophilic. An example that you might not have seen there on the end, something called an imine. This is where we have a carbon-nitrogen double bond. But you can see that it looks kind of similar to a carbonyl group, just that we've changed the oxygen out for a nitrogen. The nitrogen is still much more electronegative than the carbon is, and so we end up with delta negative on the nitrogen, delta positive on the carbon. And so because they all have that delta positive, that electron deficient carbon, they are electrophilic. The electrophile may also be something that has a single bond to an electronegative atom. So ones that you'll have probably seen, hydrogen chloride, for example, HCl, methyl chloride, CH3Cl, or just simply molecular bromine, Br2. Here, if you take HCl, the chlorine is much more electronegative than the hydrogen, so it's delta negative on the chlorine, delta positive on the hydrogen. Likewise for the methyl chloride, the chlorine is more electronegative than the carbon is, so delta negative on the chlorine, delta positive on the carbon. And for the bromine, while we have an actual 100% covalent bond here, there's no difference in electronegativity, it's not a polar bond, we of course always have the ability to have instantaneous dipoles. So our electron density in our molecule is constantly kind of moving around, and at some point there will be a point where we have the electron density further over to the right than on the left, and so we have this kind of instantaneous dipole of a delta positive on the bromine on the left, a delta negative bromine on the right. And so we have this instantaneous dipole, which can then go on to induce dipoles in other bromine molecules. But the key thing is typically it's either an empty atomic orbital, which we don't often see that often to be fair, or more commonly either a completely positive atom, something like a carbocation, for example, with an actual positive carbon, or something that is bound to an electronegative atom, either double bonded, for example in carbonyl groups, or single bonded. So we can then draw out some general mechanism guidelines, and these will apply to every mechanism that you will ever see. When we draw our arrows, the start of the arrow has to show the source of the electron pair. And so this could be a lone pair. Think back to what we said about nucleophiles. This could be a lone pair. It could be a negative charge, as long as that technically represents a lone pair. It could be a pi bond, which has high electron density, or it could even just be a sigma bond. And we saw that in the BH4- anion, that it was our BH sigma bond that was our nucleophilic part. But we could always have an arrow actually starting from just a normal sigma bond, because these contain electrons. They have an electron pair in them. The end of the arrow will show the destination of the electron pair. So this could be an empty atomic orbital where the new bond will be formed. For example, if we took AlCl3, aluminium trichloride, we have that empty p orbital. It could be a region of electron deficiency, such as the delta positive carbon, that is bound either through a single or double bond to an electronegative element. So that's, for example, HCl or a ketone. Or it could be an electronegative element that can support a negative charge. And so, for example, if we were reacting our nucleophile with our HCl, the nucleophilic part would react with the delta positive hydrogen. And then our second arrow here would be to draw an arrow from that HCl bond, ending up on the Cl. That's an alright arrow, because we've started it from a sigma bond, and we've ended it at an electronegative atom that's happy to take those electrons, it's happy to support a negative charge, because it's electronegative. And so generally, electrons will always flow from a region of high electron density to low electron density. From high to low, so for example, from a negative charge or from a lone pair to a delta positive carbon. And so the best thing to do, I always think, is to start by identifying what will act as your nucleophile and what will act as your electrophile in every step. Another thing to always be careful of is that charge and atom numbers must always be conserved in any step of a reaction. So if I start off by having a certain number of atoms, they have to be in the first step as well as the second step as well as the third step and so on. And also charge. If we overall have a negative charge on the first step, we have to have an overall negative charge somewhere on the second step, and so on and so on. So just like a normal overall chemical equation, the atom numbers have to balance and the charge has to balance. Now, as I've said in the previous slides, remember that not all negative charges represent electron pairs. So while most of them do, for example, the hydroxide anion, the bromide anion, the cyanide anion, the negative charge is representing a lone pair. Not all of them do. And so the example was the BH4- anion, that borohydride anion. The negative charge didn't represent a lone pair because all of the electrons, all of the 8 valence electrons, are actually being used in BH bonds. So it would be incorrect to draw an arrow from our negative charge. The correct way would be to draw an arrow from one of the BH bonds. So it's always really, really important to make sure you still have the electronic structure of what you're dealing with in your head and not just go straight for, oh, it's a negative charge, draw an arrow. Think about what that negative charge represents. Another common mistake is to draw an arrow directly to a positive charge when that atom already has 8 electrons. So an example would be this oxonium ion, H3O+. Remember, this is always formed if we have an acid in water. 8+ never really truly exists on its own. It always goes around as H3O+. And so this might be the electrophile. In our reaction, we have some nucleophile. And what we can't do is just draw an arrow directly from our nucleophile to the positive charge on the oxygen. Because the positive charge isn't representing an empty orbital or actually really a deficiency of electrons. Because our oxygen, think about normal water, H2O, we have 2 OH bonds, that's 4 electrons, 4 valence electrons, 2 from the oxygen and 2 from each of the, one from each of the hydrogens, make 2, so 4 overall. And then we have 2 lone pairs on the oxygens to make 8 valence electrons in a water molecule. Once it's formed a bond to an H+ cation, remember that this is also a dative covalent bond. We have both electrons from one of our water lone pairs being donated to our H plus cation. The H plus has no electrons, so it has to be this dative coordinate bond. So we now have 3 OH bonds, each with 2 electrons in, but we still have one more lone pair on the oxygen. And so our oxygen already has 8 electrons, and so that positive charge isn't actually showing us that we have an empty orbital or an incomplete amount of electrons, so we can't draw our arrow directly to it. If we have something like this, the way we have to do it is to draw our arrow to something that is attached to that oxygen, in this case one of the hydrogens. The hydrogen is still technically delta positive because the oxygen is still technically delta negative, being more electronegative. So we draw one arrow to our hydrogen, and then our hydrogen can only have one bond. So if we're making a new bond to it, we have to break the existing OH bond. And this is one of our arrows that we talked about before, an arrow that starts from a sigma bond, in this case the OH bond, from the middle of it where the electron density is, and ending up on the electronegative oxygen. That's happy to accept it because it can support a negative charge because it's electronegative. And so something to watch out for is always to think that boron, carbon and nitrogen can never have more than 4 bonds. And a really, really common example problem to see is carbons that have more than 4 bonds. So typically often you end up seeing sometimes a 5 bonded carbon. Carbon can only have 4 bonds. So if we have a normal saturated carbon, if we make a bond to it with a nucleophile, we must break another bond in there to make sure that we only ever have 4 bonds on our carbon. So we said that the main sort of type of reaction that we see for our mechanisms is bond making and breaking between a nucleophile and an electrophile. But the small sort of subset that weren't were free radical reactions. And so the one that we need to know for A level is a free radical substitution. Now this is a chain reaction, and by that we mean essentially that you could almost draw this out as a circle. And so this reaction can go round and round and round and go on and on and on, and essentially can go on many, many times. And any reaction between an alkane and a halogen goes by this same mechanism. So this is one way that we can make a haloalkane from an alkane and a molecular halogen in the presence of UV light. And so the first step of this is called the initiation. We take our molecular halogen, in this case Cl2, and in the presence of UV light, this breaks up to form 2 chlorine free radicals. Now we represent a free radical with a dot to show that there is an unpaired electron. Now the UV light is essential. The UV light supplies enough energy that we can actually break this chlorine-chlorine bond in half, and we call this a homolytic fission of the bond. What we mean by that is that essentially the bond breaks completely evenly. One electron goes to one chlorine atom, the other electron to the other chlorine atom. And so we end up essentially with just 2 normal chlorine atoms, but they are really free radicals. They have an unpaired electron. We then have a propagation step, in which our chlorine free radical reacts with our alkane. In this case, I've drawn it as methane, CH4. Now the first step always abstracts an H atom from our alkane. So in this case, we end up producing HCl as well as a CH3, a methyl radical. Our second propagation step is to take that radical that we've just made, our CH3 radical, react it with more molecular chlorine. This abstracts one of the chlorine atoms, so we end up forming CH3Cl, chloromethane, our haloalkane, and we regenerate our chlorine free radical. So this is why this can be a chain reaction. The key thing that starts this whole thing off is a chlorine radical, and at the end of this second propagation step, we've reformed that chlorine radical. So it can go on again and do the same reaction, and again and again and again. You can imagine it kind of going in a sort of circular fashion, round and round and round. Notice how always these propagation steps are always radical plus stable molecule give you radical plus stable molecule. It's a good way to remember if you've got the equation right. It's radical plus stable molecule gives you radical plus stable molecule. Also note that the radical we form in our first propagation step must be the radical we use in our second propagation step. So we form the CH3 radical in the first step. That's what we then use as a reactant in the second step. And the radical that we end up forming at the end of our second step, because it's a chain reaction, must be the same as the radical that we started our first propagation with, the Cl radical. We then have our final step, which is called termination. This is where any 2 radicals come together to produce stable compounds. It removes the free radicals from the reaction mixture. And so it could be 2 chlorine radicals coming together to form Cl2, 2 CH3 radicals to form ethane, C2H6, or For example, a CH3 radical and a chlorine radical coming together to make more chloromethane. To find our overall reaction, we just have to add our propagation steps together. We write all the reactants on the reactant side, all the products on the product side, cancel out anything that appears on both sides. Our Cl radicals and our CH3 radicals appear on both sides, and so our overall reaction for this is CH4 plus Cl2 goes to CH3Cl plus HCl. So the key thing is that if we have a halogen and we have a haloalkane, a normal alkane, we can produce a haloalkane if we're in the presence of UV light. The key thing is that the UV light has to be there. This won't react in the dark. It has to be in the presence of UV light to break that initial chlorine-chlorine bond homolytically. We can also draw it out, though, as actually using arrows. Now, remember I said that a normal arrow, which has a normal head on it, represents the movement of an electron pair, 2 electrons. But a radical reaction, we have to use these half arrows, these Fisher arrows, with only one of the sides of the head on it. And this because it shows 1 electron moving. Now we always have to consider where every electron goes. So remember that when we're using a radical, for example a Cl radical, this has an unpaired electron, and so therefore we're going to have the movement of 1 electron. A covalent bond, of course, is made up of 2 electrons, and so we have to consider where both of those electrons go. So our first step is the initiation. We break that chlorine-chlorine bond. We have half arrows going from the centre of that Cl-Cl bond onto the chlorine atoms to produce 2 chlorine radicals. Again, notice I've shown it with a dot. Our second step, which is our propagation, we have our chlorine radical abstracting a hydrogen atom. So we have 1 arrow going from the dot, the free radical bit of it, and combining with an arrow that goes from the centre of that CH bond, going to where the Cl radical is. That's showing us the formation of a covalent bond. Remember, a covalent bond, 2 electrons, so we need to have 2 half arrows meeting in the same place. And then, of course, our original covalent bond, we've used one of the electrons. Where does the other one go? Well, it must end up on the other atom. It must end up on the carbon. So an arrow in the middle of the CH bond ending up on the carbon. Our second propagation step is very similar. We have an arrow from our CH3 radical meeting with an arrow which comes from the centre of our Cl-Cl bond and ends up meeting with that CH3 radical. And then the other electron in that Cl-Cl bond has to go onto the other chlorine atom. Note that these are still all half arrows for 1 electron movement. And then for an example of the termination steps, I've shown 2 of these CH3 radicals producing C2H6 ethane. And this is very simple. We just draw arrows from each of the dots, each of the unpaired electrons, half arrows meeting in the middle to show the formation of that covalent bond with 2 electrons in. So always consider where every electron goes. The propagation steps are always molecule plus radical, gives you molecule plus radical. The radical that we form in the first step must be the radical we use in the second step. The radical that we form in the second step must be the same as the one we start with in the first step. We have to have UV light, and termination is always a radical plus a radical to give a stable molecule. And if you're drawing it out as the arrows, always use the half or the fish hook arrows for 1 electron movement. The next type to look at is now a nucleophilic substitution. So we've covered our radical reactions. So now all the rest of these reactions we're going to talk about are the bond making and breaking between a nucleophile and an electrophile. And so a nucleophilic substitution reaction is what it says on the tin. We are going to substitute our nucleophile into a molecule and eliminate something else. So nucleophilic substitution mechanisms always follow exactly the same arrow pushing. Remember that arrows always flow from high electron density to low electron density. And so let's have a look at the top example here on the right. We have our hydroxide anion, which here I have my negative charge. I've also shown a lone pair here. We have an arrow from this nucleophilic part, that's our hydroxide anion, our lone pair, our negative charge, to a region of electron deficiency. Our electrophile here is the haloalkane, and the actual the electron deficient part of this is the carbon atom. Remember that we said our electrophiles might have an atom that is single bonded to an electronegative element. Well, our X, our halogen, is more electronegative than carbon, and so we have a delta negative on the X and a delta positive on those carbons. It's not shown on those diagrams, but they are there. And so our arrow goes from our nucleophilic part, the hydroxide anion, to the delta positive electrophilic carbon. Then, as we said, always watch out for carbons that have 5 bonds. So we have to break one of the existing bonds to make sure we only have 4 bonds to our carbon. The one that we break is that CX bond, and so we have that familiar arrow of starting in between the CX bond, starting from our sigma bond where our electron density is, and ending up on the X atom, the electronegative atom, that because it's electronegative, it's happy to accept those electrons and have that negative charge. And so here we've gone from an haloalkane, we've substituted a hydroxide group on, and we've ended up producing an alcohol, and we've kicked off our halogen now as an X- anion, halide anion, and this is something that we call the leaving group because it's what leaves the molecule. But overall, we have substituted our nucleophile on. This is exactly the same arrow pushing for the example right at the bottom. So again, we have a haloalkane, and here I've used the cyanide anion. That's our nucleophile, it's a negative charge representing a lone pair. So an arrow starting from the lone pair, ending up at the electrophilic carbon, the delta positive carbon, because it's electron deficient due to the electronegativity, the polarity of that CX bond, the dipole that's created. And then carbon can only have 4 bonds, so we have an arrow that goes from the center of our CX bond that we're going to break, and ending up on the electronegative X atom that's happy to accept that charge. Now in this case, we quite often see the cyanide anion being used because it's very synthetically useful. For one, we've increased the length of our carbon chain. We've started off with a 2-carbon chain in our haloalkane. We now have a 3-carbon chain because we've made propane nitrile. We end up with 3-carbon chains. We've increased the length of it. And also nitrile groups, that CN triple bond, are also very, very synthetically useful because they can be reduced down to an amine, or they can be hydrolyzed to a carboxylic acid. So they're very, very useful synthetically. The only extra thing to note is if our nucleophile is a neutral species. So for example, if it's water or if it's ammonia. And the reason this is important is our first step of this is exactly the same. So the middle example here is our haloalkane reacting with ammonia, NH3. The ammonia, NH3, is the nucleophile. It has a lone pair. So we have an arrow from that ending up at our electrophile. The electrophile is the haloalkane, and where our arrow ends is the electron deficiency, which is the delta positive carbon, again, of our haloalkane, because of that polarity of the bond due to the electronegativity difference. So we have the same 2 arrows going from the NH3, ending up at the delta positive carbon, and then an arrow from the center of that CX bond that we're going to break. Remember, carbon can only have 4 bonds. We're making one to the NH3, so we have to break one. We break the CX bond, and so we have our arrow from the middle of the CX bond ending up on the electronegative X atom. The key thing with it being a neutral nucleophile, though, is that this next species we form isn't the final product. This is a positively charged species. Remember, I said that every step of a mechanism has to balance in terms of the atom numbers, but also in terms of the charge. Now, for example, the very top example of this with the hydroxide anion, overall we have a negative charge. We have a neutral electrophile, anionic nucleophile. And so in that second step, we form our alcohol, a neutral molecule. And therefore, we need to have a negative charge somewhere to make sure the charge balance. It goes on the X, it goes on the halogen atom to make it a halide ion. In this case, we've started off with a neutral nucleophile and a neutral electrophile for the middle example. And so once we've kicked off our X as an X- ion, we have to have a positive charge somewhere to balance the charge overall and be neutral. And the positive charge ends up on the nitrogen atom. Because we have our NH3, we've made a bond to carbon, the nitrogen now has 4 bonds and therefore is positively charged. And so our second step of this is now to take another molecule of ammonia, a second molecule of NH3, and this removes a proton from that to make it into an NH2 group, the neutral ethylamine, and we end up having this ammonium salt, which is made from the NH4+ cation and the X- anion that we previously kicked off. Now this is another example of where a positive charge doesn't actually necessarily mean electron deficiency or empty orbitals. The positive charge is on the nitrogen, but we don't have our arrow going from the nucleophile to the positive charge because the nitrogen has 8 valence electrons. It has 4 bonds. We have the 3 to the hydrogens and the 1 to the carbon. These are all normal covalent bonds, and so we have 8 electrons. So there isn't actually any electron deficiency or empty orbitals. So instead what we have to do is attack the delta positive hydrogen atom. It's still delta positive technically because the nitrogen is still delta negative due to the electronegativity difference. We attack the delta positive hydrogen with our nucleophile, and then because hydrogen can only have 1 bond, we have to break that NH bond. And so we have the arrow going from the middle of the NH bond, ending up again on an electronegative atom that is happy to accommodate those electrons, that sort of negative electron density that's going onto it. Now, nucleophilic substitution mechanisms are a vital tool in synthetic chemistry because one functional group can be replaced by another. Now, once we've replaced the functional group by another one, that can often be further reacted through other mechanisms, often by oxidations or reductions. So we can see that starting from a haloalkane, we can actually immediately get to 4 different functional groups. 3 of them can be formed by these nucleophilic substitution reactions. We can use a cyanide anion to make a nitrile. We can make an alcohol from a hydroxide anion that's aqueous, or we can make an amine from ammonia. These are all nucleophilic substitution reactions. We can also do an elimination reaction, which we'll see later on, using ethanolic hydroxide anions that produce an alkene. But if we just consider the nucleophilic substitution ones, our nitrile can be further reacted, as we said, hydrolyzed to a carboxylic acid or reduced down to the amine. Our alcohol can be oxidized if we've got a primary alcohol up to an aldehyde or carboxylic acid. If it's a secondary alcohol to a ketone. And our primary amine that we form actually is also a nucleophile, so if we don't control the stoichiometry correctly or we don't have excess ammonia, this can carry on reacting with haloalkane and produce a secondary, a tertiary amine, and also a quaternary ammonium salt. And so these functional groups can be converted further by other nucleophilic substitutions, oxidation or reduction reactions. So they're very synthetically useful. Another thing to talk about, and just double check whether your exam board needs you to know the difference between this, is an SN1 versus an SN2 reaction. So SN1 and SN2 are both nucleophilic substitution reactions. The S stands for substitution, the N for nucleophilic, and then the 1 or the 2 actually refers to the molecularity of the rate law of these types of reactions. So the nucleophilic substitution mechanisms that we saw on the previous slide were all examples of an SN2 mechanism. This is the one shown at the bottom of the screen. So here I have a standard haloalkane with a CX bond. I have my hydroxide anion, and you can see that the C oxygen bond, or the carbon nucleophile bond essentially, is formed as the carbon X bond is broken. So the forming of the bond and the breaking of the other bond happens at exactly the same time. Now this is our rate determining step. We end up then in this case producing our alcohol, and we have our leaving group. And because our rate determining step is that step there, our rate law depends on both the nucleophile and the haloalkane. We have that our rate is equal to the rate constant K, concentration of nucleophile, concentration of Rx. That's why it's SN2, because there are 2 different species in the rate law. The key thing is that the CX bond and the C nucleophile bond are broken and made at the same time. If we also have stereochemistry to think about, so let's say potentially we have only one enantiomer here, an R or an S enantiomer, only one of them. If I start off, for example, with the S enantiomer, once I've done this nucleophilic substitution, I will then have the R enantiomer. And so actually I've shown this here as the wedge bond being transformed into a dashed bond being transformed into a wedge bond. So we have an inversion of stereochemistry. The reason for this is because the way this happens is through something called a backside attack. To be able to form the bond and break it at the same time, this nucleophile has to attack from exactly 180 degrees behind that CX bond. It has to attack from the back of it. And so that's again for favourable orbital overlap. And so we have to do this 180 degree backside attack, and it causes this inversion of stereochemistry. The other one, though, is called an SN1. So again, nucleophilic substitution, but it's now telling us that we only have one molecule in our rate law. And the way this works is that we start off with our tetrahedral haloalkane, our tetrahedral carbon atom. We have a rate determining step, which is actually the breaking of the carbon X bond. So that bond breaks. That then produces now a trigonal planar carbocation and our X minus. Our second step is then the hydroxide anion, in this case our nucleophile, directly attacking that carbocation. Now this is an example of where we can directly attack a positive charge, because our carbon atom only has 6 valence electrons. It has an empty p orbital. And so we can actually attack that positive charge. Now, the key thing here is that because we start with this middle step here is a trigonal planar carbocation, our hydroxide anion can actually attack from either above or below the plane of that carbocation. And so if we end up making a chiral molecule, we end up actually having what's called a racemic mixture, so a 50-50 mixture of the 2 enantiomers. And that's what I've shown here with these kind of wiggly bonds. They could either be a dash or a wedge. So the key thing is that an SN1 gives you a racemic mixture, SN2 gives you an inversion of stereochemistry, and we can see the SN1 rate law here is the rate is equal to K, and then the concentration of Rx. It doesn't depend on the nucleophile. And there are many factors that can affect which mechanism is seen, but actually most importantly, the two factors are either the sterics, how crowded the molecule is, and the stability of the carbocation, really an electronic effect, as well as potentially the solvent choice and the nucleophile. But the two main ones are definitely the stability of the carbocation. If the carbocation is very, very unstable, for example, a primary carbocation, it's probably going to want to go through an SN2 mechanism rather than SN1. However, if the carbocation is the more stable, the tertiary carbocation, it's probably going to be quite favourable to go through an SN1 mechanism. And then likewise, in terms of how crowded the molecule is, what we call the sterics, if I have, for example, the haloalkane shown at the bottom where I have 3 hydrogen atoms, very small, it's very easy for this nucleophile to get in completely 100% behind it and attack from behind. However, if I have the haloalkane at the top, I have 3 carbon groups attached to tertiary haloalkane. They're often going to be much bigger than those hydrogen atoms, and so that backside attack, that 180-degree backside attack, is much more difficult to achieve. It's harder for that nucleophile to get into the right orientation. Now, the next one to look at is an elimination reaction. And there's a couple of different times we'll see this throughout the A-level syllabus. But I've shown 2 examples here. The first is an acid-catalyzed elimination from an alcohol to form an alkene. And the second is from a haloalkane, also to form an alkene. So let's look at the left first, this elimination from the alcohol. An elimination reaction is the loss of a small molecule from the original starting material. Often, that small molecule can often be water, and it's often initiated by acid. So the example here is the acid-catalyzed dehydration of alcohols, where we end up losing a water molecule. And so the way this works is the reason it's acid-catalyzed is because the first step is we have our alcohol. This is nucleophilic, has lone pairs on the oxygen. We have our acid. This is our prototypical, a really prototypical example of an electrophile here, an H+. We said that has an empty 1s orbital. We can directly attack the positive charge here because we have that empty 1s orbital. And so this acid, this H+, will typically come from sulfuric acid in this case. And we also it's hot as well, which helps to force elimination to occur. And so we have our arrow from the nucleophilic part, the lone pair on the oxygen, attacking that H+. This now protonates our oxygen, becomes an O+, because it has 3 bonds. We then have this elimination of water, so that's an OH2 group, so we can just eliminate the water. Again, this is our kind of the familiar arrow of starting from a sigma bond, a CO sigma bond, a single bond, starting from the middle of that and ending up at an electronegative atom, in this case the oxygen, that's happy to accept those electrons. So the water is lost, minus H2O from that molecule. This now leaves a planar carbocation, so our carbon atom now only has 3 bonds, so it has a full positive charge on it. It is actually electron deficient, it has an empty p orbital. So this carbocation is unstable, and the way that it generates a stable alkene product is to lose a proton, is to lose an H+ cation. And the way this happens is to just take one of the CH bonds on a carbon atom that is adjacent to that positively charged carbon, and we draw the arrow from the CH bond, from that electron density, and here we don't actually end up at the positively charged carbon because we don't want to necessarily just move the electrons onto that carbon to make it a carbanion. What we actually want to do is form a carbon-carbon double bond. And so the way we show this is to have our arrow starting from the middle of that CH sigma bond and actually ending up in between those 2 carbon-carbon, the carbon-carbon single bond in between those 2 carbon atoms. So if we need to form an alkene product, the way we do it is to show an arrow ending between 2 atoms. Now, by losing that H+, we've also regenerated the acid catalyst. So we end up forming the alkene, we've kicked off the water, and we also regenerate our acid catalyst, the sulfuric acid in this case. So the mechanism can proceed through these kind of stepwise steps here. It can also proceed by first protonating the water, the alcohol group, the OH group, to make the H2O group, as seen there, and then the loss of the hydrogen and the loss of the water happening at exactly the same time. So it can be what we call a concerted mechanism, or it can happen in this kind of 2-step mechanism. Very similar to how we had SN1 and SN2. It's actually called E1 and E2. And so typically check with your exam board which way they want you to draw this out. But it can either happen by kicking off the water first and then forming the carbon-carbon double bond separately by losing the proton, or losing the proton and losing the water molecule at exactly the same time. The final thing to say is that elimination reactions can also occur from haloalkanes, but it's vital that the conditions are correct. So if we have cold hydroxide anions that are aqueous, this is hopefully going to force it to do nucleophilic substitution. However, if we use hot hydroxide anions that are in ethanol or an alcoholic solvent, this can hopefully force it to do elimination. And so the exact kind of thing that we saw in the alcohol case can happen here. We can either kick off our X straight away, break that CX bond straight away to form a planar carbocation, and then lose a proton from an adjacent carbon in order to form the carbon-carbon double bond, exactly the same arrows that we've seen on that example at the left. Or it can happen in concerted fashion to lose the proton and kick off the X, break that CX bond at the same time. Now the reason it has to be hot is because we don't want it to have any competing nucleophilic substitution. And so our hydroxide anion here is actually acting as a base. So in the nucleophilic substitution, it's acting as a nucleophile. In the elimination reaction, it's acting as a base, extracting a proton from the haloalkane and causing that CX bond to break, forming an alkene. Now, one of the things that we have to be really, really careful about in elimination reactions is if we have an asymmetrical molecule is used. And this is where our elimination can happen from either side of the CX bond, essentially. So in this case, I have another alcohol being dehydrated. And we can either take the hydrogen on the adjacent carbon at the left, the blue one, or the hydrogen on the adjacent carbon on the right, the red one. So this will end up forming two isomeric products, something that we call regioselectivity. Which region of the molecule are we going to be attacking? Now, the mechanism for the formation of each of these alkene products is exactly the same arrow pushing we've seen on the previous slide. And the key thing to remember for any kind of mechanistic chemistry is that while the reagents and the molecules that we use might change, the chemistry and the mechanistic way of thinking about how we push our arrows from nucleophilic regions to electrophilic regions, what's acting as the nucleophile, what's acting as the electrophile, etc., doesn't change. So while the molecules might change, the chemistry doesn't. So trust the chemistry knowledge you have. And so if I take the, here I'm showing it actually here as a concerted mechanism. So I'm showing the loss of the proton at the same time as the kicking off of the OH group here. Now in this case, this isn't an acid catalyzed reaction. I'm not showing any acid catalyst here. But the same thing happens. We lose a molecule of water. If we lose it from the red hydrogen, we take our electron density from our CH bond. We move it down, the arrow starting in the middle of the CH bond, ending between our carbon-carbon atoms, our carbon-carbon single bond, to show the formation of that double bond. And then carbon can only have 4 bonds, so we have to kick off one of the bonds, and the bonds that kick off is the COH. That bond is the one we break. And so we've lost H and OH, so we've ended up losing water. So if I use butan-2-ol and I kick off the red hydrogen, I form water, and I end up producing but-1-ene. If I do it from the other side, though, and I do it from that blue hydrogen, I end up forming but-2-ene. Now, another reason to be careful here is that, so technically the but-1 and but-2-ene are position isomers of each other. We've simply moved the position of the alkene functional group from either the 1 carbon to the 2 carbon. But we also have to think about stereoisomerism, in particular geometrical isomerism. That's E and Z isomerism with alkenes. Now, if you're not completely comfortable with this, go and look at my video series on the alkenes. But essentially what we need to look for is if we have 2 heavier groups on our alkene, and if they are either both above or below, or on opposite sides of that alkene double bond. And so here, our 2 heavy groups are the CH3 groups, the methyl groups. And so we can either have Z-but-2-ene, which is where our CH3 groups are either both above or below. Here they're both below. Or we have but-2-ene, where we have the methyl groups being on opposite sides of that double bond. So that's E-but-2-ene. For but-1-ene, there's no EZ possible because if we have 2 of the same group attached to one of the carbons, we can't have EZ isomerization possible. And so in this top example for but-1ene, we have 2 hydrogens attached to that rightmost carbon, and therefore because we have 2 of the same group, there's no EZ isomerization possible. But if we have different groups attached, there is, because remember there's no free rotation around a carbon-carbon double bond, so the Z and the E are actually different molecules. If they're both above or below, it's the Z. If it's one above, one below, it's the E isomer. Now the next mechanistic one to look at is nucleophilic addition. So this is an addition reaction. We're going to add something to our molecule. So if we have an addition reaction, we typically have some sort of unsaturated molecule. And the nucleophilic part means we're going to add our nucleophile to this molecule. And nucleophilic addition mechanisms always follow the same arrow pushing. And so this first example here at the top is an example of a cyanide anion being added to an aldehyde. So the first arrow always goes from our nucleophile, which in this case is our cyanide anion, the negative of the charge, the lone pair that's on the carbon, to a region of electron deficiency. Our electrophile here is our aldehyde, and the electrophilic part of this molecule is the delta positive carbon, that electron deficient carbon. Remember we talked about types of electrophiles, and we said that it could be something that's bonded through a double bond to an electronegative atom. And so this is an example here. We have a double bond to our oxygen in our carbonyl group, very strongly polar bond, we have that dipole, and so we have a delta positive carbon, delta negative oxygen. So our first step moves from the CN nucleophile, the CN minus nucleophile, from the lone pair to that delta positive carbon. Then carbon can only have 4 bonds, and so we have to break one of those bonds. And so we then, the one that we actually break is the pi component of that CO double bond. That's the weakest bond there in that system. So we have an arrow that starts from the centre of our CO bond and ends up at the electronegative oxygen atom. Again, it's one of those familiar arrows of starting at a sigma bond, ending up as an electronegative atom that's happy to accept the electron density. So this now generates a tetrahedral intermediate. We've started off with a planar aldehyde molecule, a trigonal planar molecule, added the CN in, we now have a tetrahedral molecule. And the key thing is, again, remember that we have to balance our atoms, we have to balance our charge. We've started off with a neutral electrophile and a negatively charged, neutral electrophile, a negatively charged nucleophile. And so overall in this molecule that we've made, we have to have a negative charge somewhere. And the negative charge is on the oxygen atom because it's accepted the electrons from that pi bond. So the second step of it is very simple charge attraction. We have our negative charge on our oxygen that represents a lone pair attacking a positive hydrogen, a proton. This could be from some acid, it could be from just water, but it just picks up a proton. This again, we can just attack the positive charge here because we have our empty 1s orbital. And this produces our stable molecule with our OH group on, and this in this case here is something called a hydroxynitrile. Now if we have aldehydes or an asymmetrical ketone where we don't have the same carbon group on either side, this will produce a racemic mixture because the aldehyde has 3 different groups attached to bond oxygen, R group and hydrogen. Once we've added our CN group on and done and picked up the proton, we now have 4 different groups attached to that central carbon. So it's a chiral molecule, it has an asymmetric carbon in there, and therefore this will exist as enantiomers. And because our aldehyde or our ketone that's unsymmetrical is completely planar, we have this again where our nucleophile can attack from above or below with equal probability. And so we end up with a 50-50 mixture. And so that's what I've shown just below with that dotted line there showing you the 2 enantiomers. Remember that enantiomers are these stereoisomers and they are mirror image forms of each other, non-superimposable mirror image forms. And when we draw out enantiomers, it's vital that we draw them out in the proper tetrahedral arrangement with the wedges and the dashes so we can draw out our actual mirror image forms. Another example is the reduction of a ketone down to an alcohol. This is using our sodium borohydride. And remember the really key thing with the borohydride anion is that the negative charge there, the BH4-, the negative charge does not represent a lone pair. BH4- has 8 electrons, but they're all used up in BH bonds, hasn't got a lone pair, so the nucleophilic part of it is one of those BH bonds. But the arrow pushing is exactly the same. Start off from our nucleophilic component, which is our BH sigma bond. Draw that to the delta positive the electrophilic carbon here, the delta positive electron deficient carbon. Carbon can only have 4 bonds, so we break the weakest one, the pi component of that CO bond. That then puts an arrow, so from starting from the middle of the CO bond onto the electronegative oxygen. And then we have to conserve our charge. Now I've not shown the sodium ion here. The sodium ion would also be in the second step, still floating around. And so our negative charge that we now have on the oxygen must pick up a proton from water or from acid, and that produces our alcohol here. So this would be the example of either reducing an aldehyde or a ketone using sodium borohydride down to an alcohol. Now, a closely related mechanism is called a nucleophilic addition-elimination. So we have the nucleophilic addition part. So the first step of this is exactly the same arrow pushing as the nucleophilic addition. So it might seem there's lots of different mechanistic types to learn, but this is nucleophilic addition-elimination. Because it has nucleophilic addition in the name, we have to have the same arrow pushing going on. And so this example here is an amine reacting with an acid chloride to make an amide. What we're going to do here is add on our nucleophile, but now rather than just adding it on, picking up a proton, and that's the end of the mechanism, these compounds will contain a good leaving group, something that's able to be eliminated very easily, and so therefore we also have an elimination part of the mechanism as well. And so that good leaving group, whatever it might be, is replaced by the nucleophile. So the first two arrows are exactly the same as the previous mechanism. We have our nucleophilic amine with a lone pair, an arrow that starts there, to our electrophile, in this case the acid chloride, which has our delta positive carbon due to the electronegative oxygen atom and the electronegative chlorine atom, both which make that carbon electron deficient due to the dipole that's created, the polar bonds. We then have to break one of the bonds on the carbon because it can only have 4 bonds. We break the weakest one, which is the pi component of that CO bond. Once we've broken the pi component of that CO bond, we then have our negative charge on our oxygen. But now the key thing is that we don't just pick up a proton, but we also have in this molecule a Cl group. This is a very good leaving group. It's able to be eliminated very, very easily. And so now what happens is our oxygen actually reforms that CO double bond. So we have an arrow that starts from our negative charge on the oxygen, representing a lone pair, down to the middle of that CO bond, showing that we've formed a CO double bond. And then again, carbon can only have 4 bonds, and so therefore our C, often what's called the CX bond, whatever the leaving group is the X, in this case the Cl. We have that very familiar arrow, like we saw in the nucleophilic substitution reactions, starting at the carbon-chlorine bond in the middle of it, and ending up at the electronegative chlorine atom. And that kicks it off as a chloride anion. Again, like we saw with the nucleophilic substitution, if we use a neutral nucleophile, we have to have an extra step in here where, in this case, we've bonded our amine onto our carbonyl. In doing so, we now have 4 bonds to our nitrogen, so it's positively charged. And so our final product here in this third, after the second arrow, we have still a positively charged nitrogen. And so we have to have a second molecule of our amine coming in, deprotonating one of the protons off this NH2R group, and that produces our stable amide, as well as this salt, RNH3 plus Cl minus. Again, always make sure that the charge always balance and the atoms always balance. And again, this is another example where we can't attack the actual positive charge on the nitrogen because it already has 8 electrons. It's not electron deficient. There's no empty orbitals. So we have to instead attack something that is attached to it. And here we have a delta positive hydrogen. The nitrogen is still technically delta negative. So we attack at this. It's acting as an acid and a base, essentially. We pull off this proton, so we have an arrow going from the lone pair to the hydrogen atom. Hydrogen can only have 1 bond. And so an arrow going from the middle of that NH bond, where the electron density is, ending up on the electronegative nitrogen atom. And this nucleophilic addition-elimination mechanism, they all follow the same arrow pushing as we've seen here. And this general mechanism applies to many reactions, including all of the acylation reactions that you will study. So another example might be the formation of an ester from an alcohol and an acid chloride. All those kind of acylation reactions follow this nucleophilic addition-elimination. And again, as I said, while the actual reagents and the molecules might change, the chemistry and the mechanism, the arrow pushing, doesn't change. Always just use these tips we've been talking about. We then have electrophilic addition. Now this is where we would have seen typically this in the alkene series of videos. So an electrophilic addition mechanism always follows the same arrow pushing. It's an electrophilic addition because we are dealing with an electrophile being added to an unsaturated molecule. Again, it's an addition reaction, so we're going to have some sort of unsaturated molecule, and we're adding an electrophile to it, so electrophilic addition. And so an example of this is our alkene reacting with lots of different electrophiles. So it could be HBr, it could be Br2, it could be sulfuric acid, it could be H3O+. And I've shown two examples here. The first one at the top we'll talk through first. So an alkene reacting with HBr. Here, our HBr is our electrophile. Remember we said that our electrophile could be something that is bonded to an electronegative atom through a single bond. Here we have HBr, which it is. So our hydrogen is delta positive, our bromine delta negative due to the electronegativity difference. It's a polar bond, we have a dipole, and this is technically a permanent dipole. We said that we could have Br2 acting as an electrophile, but in that case it had to be an instantaneous dipole or maybe an induced dipole. Here we have a permanent dipole in this molecule due to the electronegativity difference. So that's our electrophile. Our alkene must be a nucleophile, and we said earlier that alkenes could act as nucleophiles because we have our electron-rich pi component of this system. We have a pi bond, electron-rich extra electron density that can act as a nucleophile. It doesn't have to be a lone pair. So the first arrow is always an arrow from the centre of our carbon-carbon double bond, from our pi bond, which is nucleophilic, to the delta positive atom, which in this case is our hydrogen. Then hydrogen can only have one bond, so we have to kick off the other bond it's attached to. So we have that arrow of starting from the middle of the HBr bond, ending up on the electronegative atom, the bromine here that's happy to accept. And so it ends up getting kicked off as Br-. And so it's always an alkene that is electron rich, attacking some kind of delta positive atom which is electron deficient, electron poor. Once we've done this, we now generate a carbocation. So we've broken open that CC double bond. Our hydrogen is attached onto one of the carbons, but the other carbon now only has 3 bonds. So we've made a carbocation. This is technically an electron deficient carbon. It only has 6 electrons, so it's got a positive charge, and it's a carbocation, which remember is plain. And then our second step here, the arrow is very simply a very quick charge attraction between our electronegative atom that we will have kicked off in that first step here, the Br-, to the carbocation. We go directly to that positive carbon atom because it is electron deficient. It has an empty p orbital, only 6 valence electrons, so we can draw it straight to that carbon atom. And that's our electrophilic addition mechanism. We started with an alkene, we've ended up with a haloalkene. And it always follows the same arrow pushing, as we've just talked about there. Another thing to note is the orientation of the electrophile, in this case the HBr. You can see that while the alkene is kind of drawn sort of side-on, going from left to right, we've drawn our electrophile as kind of going almost kind of vertical, if you like, going from top to bottom. So the electrophile, essentially, you can look at there as being drawn at right angles to the CC double bond. And this is really important. If we drew the electrophile also kind of side-on, we would have a region of positive charge next to our double bond. That would be favourable, charge attraction. But we'd also have a region of delta negative close to our double bond. That would be repulsion. And so that's a much higher energy scenario than having it drawn in this direction, where our delta negative bromine is far away from our carbon-carbon double bond, our electron density, and our delta positive hydrogen is the one that is closest. Another example would be to draw it using, so this would be an example with H3O+, that's the oxonium ion. This can be made from water and an acid catalyst, so if you have a dilute solution of an acid, this is what exists, H3O+, not H+. But the arrows are exactly the same. Remember, we talked about having this H3O+ molecule that we can't attack the oxygen directly, the positive oxygen, because it's not electron deficient. I've not shown it here, but the oxygen has a lone pair still. And so we have 3 of these OH bonds, a lone pair. It has 8 valence electrons, and therefore it's not electron deficient. We can't draw our nucleophilic arrow to attack that. And so instead what we do is what we've seen before with lots of other examples. We attack something that is attached to it. So we have our alkene, the pi bond of that, the electron density, the nucleophilic part, attacking the hydrogen atom that's attached to it. That's still technically delta positive because the oxygen is delta negative. And then hydrogen can only have one bond, so we break that HO bond, starting from the middle of the HO bond, ending up at the electronegative oxygen. This then generates again our carbocation. So one of the carbons picks up that hydrogen atom. The other carbon is left electron deficient with 6 electrons, so a positive charge and a carbocation. And then we have the same arrow pushing as we saw before. So the thing we've kicked off, in this case it will be a lone pair rather than negative charge. but that lone pair, starting from the lone pair and arrow, going to that the actual full positive electron deficient carbon. Now again, because we've got this kind of neutral nucleophile in this case being added in that second step, we have to lose a hydrogen atom, and in this case we can just draw it as one of these hydrogen atoms sort of being kicked off as a proton. So an arrow that goes from the middle of our OH bond ending up on our oxygen, that makes it a neutral alcohol at the end, and because we've lost our H+, we've regenerated our acid catalyst. Now again, we have to be a bit careful, like we saw with elimination reactions. If we had an asymmetrical molecule, we had to be careful about which side of the CX bond we did our elimination from, and we ended up with isomeric products. The same is true for an electrophilic addition reaction. If we have an asymmetrical alkene, this will produce a mixture of products. Again, we'll end up with isomers, and again, normally position isomers. So the formation of all of these products that we see here is exactly the same as we saw on the previous slide. The arrow pushing is exactly the same. And essentially here in this we have propanone being used. Now our hydrogen atom can either go onto the leftmost carbon or to the rightmost carbon. If it goes onto the leftmost carbon, we form the carbocation at the top. This is a secondary carbocation. Remember, this primary, secondary and tertiary relates to how many other carbon groups are bonded to that positive carbon. So we have two other carbon atoms bonded, so it's a secondary carbocation. If the hydrogen atom goes on to the rightmost carbon of that double bond, then we end up with a primary carbocation. And remember that we talked about, again, go back to the alkenes video if you're unhappy with this, but we talked in that video about the stability of the product being rationalized through how stable the carbocation is, and through something called the positive inductive effect. This was this idea that alkyl groups are slightly electron releasing. They kind of put their electron density onto that positive carbon atom, and therefore that lowers the energy of this carbocation. So the more carbon groups it has attached, the more positive inductive effects and the lower energy that carbocation is, and therefore the more stable it is. And so because we have our secondary carbocation with two positive inductive effects, that is more stable than our primary carbocation with one positive inductive effect. Our second step is the same for both, that charge attraction here between the Br- nucleophile and the carbocation electrophile. At the top from our secondary carbocation we end up with 2 bromopropane. At the bottom from our primary carbocation we end up with 1 bromopropane. And the 2 bromopropane is the one that is the major product because it comes from the most stable carbocation. Now, it doesn't necessarily mean that we only form that product. This is this idea again of regioselectivity, which region essentially of the double bond do we attach the things onto. It doesn't mean that we just form the 2 bromopropane, we would get a mixture. That's why we have a major and a minor product. But it probably would be that the 2 bromopropane might be in 75% and the 1 bromopropane in 25%. And so again, the stability comes from the stability of the carbocation due to the positive inductive effect. And so we have to look for the number of carbon atoms that are attached to our positive carbon. And again, the alkenes and the electrophiles may change, but the general mechanism and the way we push our arrows is always the same, because we're thinking about these general mechanism guidelines of how we push our arrows and what our nucleophile and electrophile is. And then the final one to look at is an electrophilic aromatic substitution. So here we are substituting one of the hydrogens on our benzene ring or aromatic ring for our electrophile. So it's essentially an electrophilic substitution, and because it's happening in an aromatic system, it's an electrophilic aromatic substitution. And these reactions always follow exactly the same arrow pushing. So I've got an example here of the nitration of benzene, putting an NO2 group on it, and also the Friedel-Crafts acylation of benzene, putting this acyl group on. So if we talk through the first example here at the top, the nitration, the first arrow is from one of the double bonds in the benzene ring, ending up at the electrophile. So our benzene actually is acting as our nucleophile. Think of it like a sort of extended alkene. We have in benzene we have this very delocalized pi system around all of the 6 carbon atoms. This kind of 1.5 bonding around all of the carbon atoms. Sometimes you may see it drawn as a hexagon with a ring in the middle, as opposed to 3 single and 3 double bonds. Just check with your exam board which way they want you to draw it out. I'm drawing it out here as single and double bonds, but the mechanism is the same if you do it with the ring in the middle. And so we have our benzene here with our delocalized pi system acting as the nucleophile, electron rich. We have our NO2, our electrophile, a positive charge here on this electrophile. It's a positively charged species. And so we have our arrow very simply from our nucleophilic part, which is a double bond, if we're drawing it in this localized structure, ending up at our electrophile, which is our positively charged NO2. Now again, just double check with your exam board on how they want you to show this. If you're writing it out just as NO2 plus, that first step is done. However, if you write it out as a full, kind of the NO2 expanded out, NO2 is actually nitrogen with oxygens on either side, both double bonded, and so the nitrogen is positively charged. If you're drawing it out in that direction, which is the more technical direction, you can attack the positive charged nitrogen, but you have to break one of the nitrogen-oxygen double bonds to make a single bond out of that. So again, remember we said that nitrogen can never have more than 4 bonds. And so we have to, once we form the bond to nitrogen, we have to break one of those NO double bonds from the middle of the bond, ending up on one of the electronegative oxygen atom. So just double check with your exam board which way they want you to draw this out. But then, no matter how we've drawn it out in that first step, the second step will look like this. So again, you can imagine it being very similar to the electrophilic addition reactions we've just seen. When we attack this NO2, well, the NO2 will be attached onto one of the carbons where that double bond was. The other carbon will now have a positive charge on it. It's electron deficient. And so our second step is always just to reform this double bond, to reform the aromaticity to make it a delocalized system again by losing a proton, by losing an H+. So we have an arrow that goes from the center of that CH bond, ending up between the 2 carbon atoms to show the formation of a carbon-carbon double bond. Now again, it's just the reason why we do this is in the first step we've actually broken the aromaticity. The aromaticity meaning we have that delocalized electron system, the electrons spread out around all of the carbon atoms. By making a bond to that NO2, we've broken that aromaticity. That's a really, really big energy gain. If you go back to my video, energy penalty, sorry. If we go back to my videos on aromatic chemistry, you'll see that there's a really, really big energy gain from being in this aromatic state. If we break it, that costs us lots and lots of energy. But typically what we can do is break it in one step and then reform it in the next. Then overall there's no actual really loss of energy, essentially, because overall we've regenerated that aromaticity. So generally if you break it in one step, always reform it in the next. And so that's what we've done. We've broken it by attacking our NO2. We've reformed it by losing that proton. The same arrow pushing happens if you look at an acylation reaction, a Friedel-Crafts acylation. Again, here we take an arrow from our nucleophilic benzene ring to our electrophilic molecule, which in this case is our psyllium ion. Now here, we can't attack the positively charged oxygen because that isn't electron deficient. It still has a lone pair on it, which again I haven't shown, but it has a lone pair plus the triple bond, so it has eight valence electrons, and therefore it's not electron deficient. And so we attack the carbon atom, and then we break one of the pi components of that triple bond. Carbon can only have 4 bonds, so that's why we have to break one of those pi components, an arrow from the middle of that CO triple bond, ending up at the electronegative oxygen atom. Once we've done that, we've added our acyl group on, but we've broken the aromaticity. So we have the acyl group being added onto one carbon, the other carbon being fully positive, electron deficient. And so we reform, in this case, that double bond, essentially reforming the aromaticity by losing a proton. An arrow from the middle of that CH sigma bond, the CH single bond, ending up between the 2 carbon atoms to form that carbon-carbon double bond. And remember that when we do our acylations, we can always get back down just to the alkane chain by doing a reduction, either using zinc or mercury and HCl. So just always double check with your exam board whether it requires you to draw the mechanisms using the localized structures like I've done here with 3 single and double bonds, or the delocalized structures, which is where we have a ring in the benzene molecule. Now if we use a ring, the arrow pushing is exactly the same. In the first step, we draw an arrow from the center of our benzene ring, the center of that hexagon with the ring in, to our, in this case, for example, the NO2 electrophile. So there's a very slight difference in that we don't go from one of the double bonds to the electrophile, we go from the center of the center of that aromatic ring to the electrophile. And then in this localized structure, it's very easy to draw out the two double bonds that haven't changed, and the one that has. One carbon has a positive charge, the other has the NO2 attached on. If we're drawing a ring, what we have to do is the carbon that will be positively charged, we don't draw a ring from, and the carbon atoms that are adjacent to it on either side, that's where our ring starts and ends. So we have an incomplete, kind of like a semicircle that we end up drawing out to show that we don't have that complete aromaticity. And then our second arrow would still go from the centre of that CH bond, but would end up going into the middle of that hexagon to show essentially the aromaticity being reformed. So just double check whether your exam board wants the delocalized structures or the localized structures. I would always recommend drawing the localized structures because they're much easier to draw and actually much easier to use mechanistically. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found the video helpful, please leave a review on a tuition website. I offer online tuition for chemistry, so please check my tuition pages for prices and how to contact me. And if you need any more help with your chemistry, you can always feel free to drop me an email. I'll be happy to help.